Okay, so in this video, we're going to be learning how to code and learn about arithmetics, plotting, and functions. First, let's start with arithmetics because it's the most simplest. But before we start this video, make sure to like and subscribe. Okay, let's do it. Okay, so first we're going to do some simple arithmetic like 1 plus 1. So / means it doesn't. The computer doesn't know what this is. Anything after // the computer just ignores. So like if I do / thinking is bad, it won't matter. So here we're doing 1 plus 1. So here we can code the function 1 space because we need social spacing plus 1. This arithmetic code is very simple because it just adds 1 to 1 and shift enter, you get 2. But in computer there is no x. X symbol means variable, so there is no x. Instead we use a star here. So we do 2. So in this instance we do 6 times 6 times 2, which will give us 12. And here we have 6 divided by 2. This obviously equals to 3. But if we do 6 divided by 4, which is 1.5, it will only give us 1. This is because we gave it integers. If you give the computer an integer, it has to give you an integer back. So to solve this problem, we add 0.0. This is a decimal that equals statistics, and look what we do now, 1.5. So for these hard ones where it's not possible by integers, we use 0.0, or known as a double. Here we have defining a function. This line of code or cell defines x. X is a variable or unknown number, which x is unknown number, which means it can be anything from 1 to like infinity or negative infinity, if that's even a thing. So here we have decided that x is going to equal to 1. So here we have the simple function x plus 1. Now you may be wondering what is x plus 1. X is 1 plus 1, then it will equal 2. Oh wait, no, I need to find this first. Now it will equal 2. Because x is equivalent to 1, so this is name. It can be any number, but we'll use x because it's easy, plus 1 equal 2, because x is equal to 1. We can change this number to be like 2 or something, so it will equal to 3. And we can also do x plus 1, which we call this function twice, so it will be 1 plus 1 plus 1 equal to 3. Now we're going to be learning about functions. So function is something when you give it a input and gives you an output. Now we're going to show you some examples of functions. So look, this function is Iron Man, Tony Stark, Captain America, Steve Rogers, Spider-Man, Peter Parker, Doctor Strange, Stephen Strange. So this function is basically giving the fake name to its real name. So this function is converting Iron Man into Tony Stark, because Iron Man is the fake name, and then Tony Stark is the real name. Same thing here. Harry Potter goes to Gryffindor, Harry McCrellin goes to Hufflepuff, Ronald Weasley goes to Gryffindor, and Hannah Albott goes to Hufflepuff. So this function is basically sorting students into their correct house. So these are some more interesting functions and how to code them. So the first is the string function, or the same function. In this function, we named the function name is same. So and then string just means like line of text. So if we type same, which is the name of the function, put brackets and then put apple. When we submit this code, it will give us apple. We can change this to anything. So instead of hello, we can change it to the cow. Now it'll give us the cow back. That's a thing with functions. So you can name this anything. like that, it will give you this back. Now, the string now it's the identity function. Identity function is you give it a number, it gives you the same number back. So it's not really interesting. So if we had identity 0.1, we submit it. It just gives us 1. We type like 89, give us 89. We type this number, it gives us the number. So that's the identity function. And like that again. So that's the identity function. Now, but that's not really interesting. It's just giving us the same number back. But now we're doing this function. It's as an add 1 function. You can call it anything, but in this case it's add 1. This is giving us return x plus 1, which means when we set something to x, it will plus 1 to it and give us the answer. So in this case, we call the function, which is add 1 because it's the name, then put 0, 0 in bracket. So this means 0.0 is x. And then this function basically gives us x plus 1. So we do that and call the function upon it. It will give us 1. If we change this to 5, it should give us 6. It's just plussing 1. You can also change this function to like 3. So when you do that, when I put 5 again, it should give us 8. You say this is basically calling the function twice because of add 1 and then add 1 again. Anyway, but no, this is just a name, so even if it's like add 3, it still works because that's just the name of the function. You can change the name by just changing it like add 3. Then you have to submit the code again and change these to add 3. Add 3, so it should give you 6 because it's basically x is 0 and it's adding 3 twice. Because that's what the function is coded to do. This is basically the same thing, but it's adding it 3 times, so it should give us 9. Now we're going to be learning about plotting. Okay, so now we're going to explain to you what coordinates are and the address of each point. So, there's the x-axis is the horizontal line, or this thing here. And the y-axis is the vertical one here. Each point has a name or address. The address for this is 2, 2. So it's 2 from home, 2 from 0, there, and 2 up, so there. And then you combine it here. So that, and then -1, -3. So you go -3. So you go 1, you go here, and you go -3. So here. So that's the point. -2, -4. You go -4 here, and you go -2. Which is like down 2, so it's here. So each point on a coordinate system has an address defined by 2 numbers, the x value and the y value. I'll show you how to plot some points here. So this is plotting. What if he thinks yx? What do you mean it's yx? I'm showing him here, you stupid dingus.
Don't you have to do it here? Why are you doing it on the code?
It's literally so much more clear here.
Right.
It's dingus. Right, you can literally do it here. It's literally superior. Look, this is a point, and this is when x equal to thing and y equal to thing. How does he know x is always 1?
Well, how does he know it's y first? What if he thinks y1, x1?
That's what I'm going to explain here, you dingus.
Do it here, you dingus.
I don't know, can you crop this?
Wait, this is false.
So here we're going to plot some points. So x is always first before y because it's just how the way things is. So here we have x1 and y1. This means x is 0.1 and y is 0.1. See, this x is this vertical line. So look, as shown it is 1, and then the height is 1 or y. So this is a point. A point is just a single dot, but you can add more points. If you have 2 points or above, you can make a line. A line is 2 or more points joined together by a line. So in this case, it is point 1 and 2. As you can see here, x1 and y1 is here because x, y1 is here. And then 2, it's like 2 and 2 here. This can also be changed like this. This can be like 2. This can be like 3. This can be 1. And this can be 2. 2 here. So now look, 2, 2. So 2, 2, and 3, 1. These numbers can go into decimals as well, or negative numbers. Negative numbers is just a tiny bit trickier because you have 2 sides. So like this. So you can make it -2, -2, like this. And you'll see it goes down here. So -2, -2. This can also be decimals, like this. 0.5. 0.5. So it'll give you like this. So it'll give you 2, 2, which is here, and 1.5. 1.5. X is 3.5 for X, so it's here. This is 3.4, so this is 3.5. And 1.5 is here, so it's here. You can also add negative decimal numbers, but it's literally the same concept. So look, negative decimal here. So that's how you plot plot the stuff. So now we're going to be looking at linear functions. So a dot is a 0-dimension thing. It's just a dot. Now a line, two dots make a line, or 2 points make a line. Any 2 points make a line as long as they are not on top of each other, like right overlapping. Then any 2 points make a line. Here are some more examples of lines. All the points lie on the same straight line of the thing. And here's more examples of straight lines, because we like straight lines. So the main formula for linear equations is the thing y equal to mx plus b. M is basically the slope. It rotates the slope up and down like that. You can do like that. It's not really clear, but it'll get more clear when we go into the coding. And then the B moves it up and down on the y-axis. It's like shifting it up and down. It will also be more clear when we start coding it. So let's start that. So first, before we get into that, let's start with the simple thing, just making a linear function. So here, first we start by making the function y1. The name is y1. So this is basically the identity function I did earlier in the video, so make sure you go watch that again. And also, so it's basically an identity function. So y1 is just basically returning x. So whatever x is, y is x. That's what it means. So let's create the x values. So this is just a name. You can name it anything you want, but we're naming x values because it's clearer. And then the x values range from -20 to 20. And then we're timesing 1 to the x value, 1.0. That just makes like a 0.0 at the end because it's more clear. It just makes it into a double. So, and then if we submit the x values like that, we submit that, and then we do that, that will give us the code. So, -20 times 1.0, that's just 20.0. So these are all the x points that we're going to be plotting. And now to make the y points. The y values, the y1 value, the y values, basically like the straight line up, the verticals, it's the x values, and then this part basically means you're getting the x values and applying what you're calling the function y1 onto it, which just gives you the same thing, because y1 is just the same thing as x, and like this function says. So if we get that, it should be the same thing as the x values. Now, if we put that into code, so this basically means, these two lines basically mean the x points are set for the x values. The x values are basically just this, that. So the x points are this, that, and the y values are basically this, the same thing, but the function y1 called upon it, which is basically this identity function. So it's the same thing. So now we can plot it out, and look, it says look 2020. See, just a straight vertical line. All the points are on the same line. And then the same thing, look. X is 20, Y is 20. X 20, Y 20. So that's what it means to plot the thing. So now we're going to make a different function. You remember the function y equal mx plus b? So this is x and this is the b. This b is shifting up and down on the y-axis. We'll show you more examples of this by changing the code. So first we're adding 1 from x. This function basically is x but plus 1. So the x values, x means x values here. X values this. So it's this and this. So the y values equal the x value, which is up there, but instead of using the y1 function, we use the y2 function. So it's basically all the x values but plus 1. Because of it, so it's all the x values plus 1. So that means this will be minus 29, this will be minus 28, this will be minus 27, and so on. That means, so now we set x values and y2 value because we changed the thing, and now look what we get. If we plot this, we get, look, 19, 30, 19, 29, 18. So this is the x values here. And yeah, so but now we're going to change the offset. So right now the offset here is 1. Let's change it to like 5 so you can see the changes. See, now when now because we changed the offset, the lines always intersect at the point 5. The first intercept always at the point 5. Like here, -5 in this instant because it's plus-ing the thing, I'm pretty sure. So -5. We're doing the slope now, which is times x, which is a random number. So this function is called y3 because y value is 3. So y value is 3 is equal to x values, which is all the way up here. And it is adding the function y3, which means return 2 times x. So if we submit some code here and then do this, it should be like a giant line here because we changed the offset to like 100 over here, so we're just gonna decrease it back to 1, although it's gonna be too big. So here we go. Submit this again. Look, it's way smaller now. Here, from 9 to 100. So first we're gonna change this point to some more easier points to understand. Let's change this to negative 10 to 10 because it's easier. And there's some code. So here we have the line. Yeah. So you see this line, right? There is no offset because we didn't add one here. But the offset is always at 0 because we never add one. But this is slightly sloped here, or the rotation. So we can make this a little more sloped if we change this. So let's see, we change it to 10. As you can see, so here is still the offset. So let's say the offset is, let's say 5. The slope is 5. See, look, now it will like slightly rotate in that direction. Let's change to something more obvious, like 10. Now it will rotate more clockwise. If you add a minus, it will basically just rotate the other direction, like this. So that's the slope. That's how you code linear functions. So the main equation for linear functions is the equation y equal to mx plus b. So m is like the slope. It's like the slope how it rotates, and b is like how up and down it moves on the y-axis. So I'm gonna change this to show you a few examples. So when m, or the slope, is equal to 1, you can see it rotates a bit like that. It went from the straight line a little bit upwards. Change to 5. Change it to 5. you can now see it's changing more for negative numbers. It does the same thing but the opposite way. So we put minus negative 5 here, negative minus 5. It just basically rotating the other way. Now we will show you the offset. So the B is the offset is how you move where the line intercepts on the y-axis, or basically just moving it up and down on the y-axis. So if we change this to let's say 1, you can see it rises from the line a little bit by 1, but it's not very visible. So we'll increase it to 10. As you can see, it has risen off the line by 10. The thing is, we can do both of them at the same time. So this can be 10, and this can also be 10. So as you can see, it's rotated by 10 from 0, and it's risen on the y-axis by 10. As you can see, it intercepts the y-axis at 10. This doesn't count because it's the x-axis, not the y-axis. The straight one up here is the y-axis, and that is the x-axis. So it intercepts on the y-axis. We can change this to say 50. As you can now see, it intercepts on 50. It's rotated by 10, and it intercepts the y-axis on 50. So now we're going to be doing Galileo's equations of motion. But before we start that, we're going to tell a little bit of Galileo Galilei. Galileo Galilei was the first person to combine physics and mathematics into one. He's the one that proved Aristotle wrong. Aristotle's theory was the rock falls to the ground because the rock likes the ground. The feather doesn't really like the ground, so it takes longer for the feather to touch the ground than the rock because the feather doesn't like the ground that much. That was Aristotle's theory, but Galileo proved it wrong. Galileo actually discovered that a feather has the same fall rate as a rock. The reason why a feather falls slower is because of air friction. The rock bursts through the air friction while the feather floats on the air friction. So that's why the feather flows slower than the rock. So motion. So this diagram basically means, so at the very start, when it's at its very starting point, the first velocity is v0. V0 is just a name. It's called velocity 0 is just a name. And then the position is x0, which is just a random, it's the very start of the thing. The time is x0. X0 is just a name, so you can name anything you want. So after time t, so like a certain amount of time, t time, it will reach, there's a new velocity, which is velocity 1. It's just a name as well. You name it anything you want. But this v1 is just basically a velocity different to v0, which is the first velocity. And then x1 means that it's changed position. It's changed position. So that's the first position. X0 was the first position, and x1 was the second position. So imagine a surface with no friction, and there's a ball on the surface, and you roll it, and then that ball never gets any more force, and no friction slowing down. That ball will move as something is called a constant speed. A constant speed is when something moves at a speed that doesn't slow down or doesn't get slower or get faster. Speed is basically how much distance something can travel in a certain amount of time. And the formula for speed is v velocity or speed, whatever you want to call it, equals to distance over time. Here's an example. A rabbit runs 10 meters in 2 seconds. its speed is 10 meters per 2 seconds. So in 2 seconds, it will run 10 meters. But we can actually make this more accurate. 10 meters divided by 2 is 5 meters. So the rabbit's more accurate speed is 5 meters per second. So this 5 meters per second basically means that every second, the rabbit will travel 5 meters. And also, the distance is basically the accumulation of speed over time. D equals V times T means V plus V plus V plus V T times. So it's basically and V is velocity. So it's basically accumulating V, or the velocity is speed. So it's basically accumulating the speed over time. So distance is how far something travel per unit of time. So example of distance is 1 centimeter. If I step 1 centimeter in 1 second, I travel 1 centimeter in 1 second. Now the formula or the equation for distance is D equal V times T, or distance equal to velocity times time. I'll show you an example of how that works. So let's say, try to figure out the time, okay? And we know the velocity is 3 meters per second. 3 meters per second. And he traveled 3 meters per second for, let's say, 4 seconds. Okay? Like that. Now, for 4 seconds. Now to compute the distance, we do 3 meters per second times 4 seconds. See, now meters per second times second. So the two s's cancel each other out and actually make meters. And then 3 times 4 is 12. So that's your answer. So the answer to if the velocity is 3 meters per second and he traveled 4 seconds of doing 3 meters per second, he traveled 12 meters in total. And that's how you get the distance. So acceleration is a rate. It measures how speed changes in time. Acceleration, or short for it is A, is equal to the difference in speed divided by time. This is equal to V1, the new velocity, minus the old velocity, or the starting velocity, divided by time. This can also be written as V1 equal to the starting velocity plus acceleration times time. Acceleration times time means A plus A plus A plus A T times. And it's basically adding it to V0. So after you have this A plus A plus A, you add it to the starting velocity and it'll give you the new velocity. Now we're going to go and do some examples so you can see better. Open PowerPoint. Okay. So the acceleration can be written as a formula: A equals to delta V over delta T. This basically means acceleration is equal to the changes in velocity over the changes in time. So if we plug in some random number, as you can see, this equation will work. This can also be written as V1 minus V0 over T1 minus T0, which is basically the same thing as I just told you. So let's plug in some random number and see if it works. So let's say dV is equal to, the difference in time is equal to 5. And let's say the difference in time is equal to, let's say, 1. Because right now we're going to start off with an easy example and it's going to get harder for the second example. So if dV is 5 and dt is 1, it can be also written as A equal to 5 over 1. Because we're just replacing dV and dt with the numbers, because it's equivalent to the same thing. So at first you do this thing, which is 5 divided by 1, which is obviously 5. So we can write this as a equal to 5, which means this kid is accelerating at 5 meters per second, like this. So before we get into the codings, I want to do a quick summary of the theory. So D equal to V times T. This basically means that there are T copies of V. So like V plus V plus V plus V plus V T times. So this is why D is equal to the summative of V times T. Likewise, V equal to A times T is equal to A plus A plus A plus A T times, like his. This is also why the summation, the accumulation of V is equal to A times T. So here we have the speed function. So this function basically has two things. It is the acceleration and the time. This function basically is the start. It basically is telling you to add v1, which is the new velocity, is equal to the starting velocity plus the acceleration times the time. To get the distance of a function that the speed is waving around the place, you get the average velocity. To get the average velocity, you get the starting velocity and the ending velocity, add them together. So like the ending velocity, starting velocity, you add them together, plus them, and then you divide 2 or cut it in half. You divide it by 2, and that's how you get the average velocity. So this is basically what this function does. This one is velocity average 1, which is basically just it still gives you the starting velocity, but instead of giving you the ending velocity like the last one did, this one, it gives you the ending time. From the ending time, you compute the ending velocity, and then with the ending velocity, you can do the starting velocity plus the ending velocity. You combine them together and you cut it in half. So that's basically what this function does. So the distance to function, which is the name of this function, is basically just timing the velocity average by time, and you get the distance. So this one is just plotting it. It's going much faster. It's going way faster than the other one. This is constant acceleration. Because this is called constant acceleration. Constant acceleration is basically just accelerating at a constant pace over and over again. Because instead of applying the distance 1 function, we applied the distance 2 function. Unlike this one applied the velocity average 1 function, we applied the distance 2 function here. So that's basically what this does. And then now let's plot the 2 plots on the same curve. We're going to be comparing this one to this one. So to plot them on the same curve, we first set the t values 0 to 20. Then we do the trace is just the name known. This is the scatter function, which scatters the points around the graph. The x values are going to be set as t, and the y values are going to do the distance 1 function. The distance 1 function is the constant speed function. It's up here. The distance 1 function basically locks the speed for 0, so the t stuff and the t is the time. So it's basically 0 times 5, 1 times 5, 2 times 5, 3 times 5, 4 times 5, 5 times 5, all the way to 20 times 5, because that's the t. Dude, this should give us like 5, 10, 15, 20. 0, 5, 10, 15, 20, 25, 30, like that. And then this one, trace 1, is just another scatter function, scatters the points, t. But this one is applying the distance 2 function. Distance 2 function is the constant acceleration function. So it's constantly accelerating up. And then, by these functions here, those are called there's a name function. They just name it. So like constant speed is the blue one, that one, the slow one. and constant acceleration is the orange one going up. And then this is plotting it on the same graph. So we do this trace one, which is that, trace 0, and trace 1, plotting them in there, and then shift enter. There you go. And then that will plot them on the same graph. And now you can see the difference between constant speed and constant acceleration. So now we're going to be teaching you the relationships between speed and distance. But first, you know how you've been using the thing d equal to vt. But that is assuming that v is a constant speed. Like the speed is like 3. That is assuming v is a constant speed. But now v is going to be in the changing speed. So it's going to be like 3, and then like 5, and then like 2. So it's going to be changing now. First, what is the relationship between these two curves? If you don't know, we're going to teach you. But first, I'm going to teach you how to read a speed graph. So the speed graph has basically two things. So here, right here, this vertical thing here, that's the velocity, and this here is the time. So to read a speed graph, the first thing you need to do is this. That means it's traveling 1 meter per second, or for 5 seconds, because that's from 0, 1, 2, 3, 4, 5. That goes from 0 to 5 on the time. And then this is traveling 1 meter per second, because it's 0, 1, 2, 3, 4, 5. It's 1 meter per second, and that's traveling for 5 seconds. So that's how to read a speed graph. This is 5 meters per second, because the line is here. It's 5 meters per second for another 5 seconds, because 5 to 10 is 5. And then that is 3 meters per second. 3 meters per second, because 3 is here and that. And that's how you read a speed graph. So now we're going to be learning about a leg. A leg is basically when the speed changes, it makes it look like a leg. So an example of leg is like here. There's 3 legs in this speed graph here. The first leg is 1 meter per second. The second leg is 5 meters per second. And the third leg is 3 meters per second. Like that, you can see the 3 legs here. First leg, second leg, and third leg. But now we're going to teach you how to get the distance of each leg. So the first leg is basically just normal thing. D times V1t. Which is D equal to V1 times t. Or V1 is just a name, it's just the speed. It's just like a speed. That's the distance and that's the time. So to get it, you times the speed by the time. The time is V1, and the time is t. So this equation right here is basically timesing V1 and t to give you a point on this graph. So like an example is, since the first leg is like 1, so V1 is 1. 1 times, let's say you did it for 3 seconds. So you did it for 3 seconds. So it's 1 meter per second. So that's V1. 1 times the time, which is 3 seconds, which is t. So 1 times 3 is 3. So distance equal 3. So it's somewhere, it's here. So the distance when the time equal to 3 is 3. Now for the second leg. The second leg is this thing right here. And to compute the distance for the second leg, you do this equation. D equal to V2. V2 is just a new speed. V2 is just a name. Change anything you want. It's just a new speed than V1. T minus 5 is basically the time from here to there. That is T minus 5. And plus distance 1. Because distance 1 is just here. It's where the other one left off. Is where this leg 1 left off. Distance 1 is from 0 to 5. That is distance 1. And this is just this. So that is how you get the second leg. Now let's do some example. Now the example is, let's say t, the time is 7, and the velocity is 5 because it says right here on the speed graph. So the time, when the time is 7, so 7 minus 5 is 2. And then 2 times 5, because the velocity is 5, is 10. So that's 10 distance plus d1. d1 is 5. Because leg 1 is 5. d1 is 5. So 10 plus 5 is 15. So when the time equal to 7, the distance is 15. It should be right here on the distance graph. Now for the third leg is this thing. And to compute the distance for the third leg, you do this equation. T equal to velocity 3. Again, velocity 3 is just a name. You can name it anything you want. T minus 10. T minus 10 is basically the time from here to there. And then plus D2. D2 is this. It's where you left off last time. So like here. Right here. That is D2. Distance 2. So it's like here and that. 10 seconds. So that's how you do it. Let's plug in some numbers so you can see. Let's say this is 14. T is 14. And the velocity is 3 meters per second, as you can see on the speed graph. So 14 minus 10 is 4. And then 4 times 3 is 12. And 12 plus 12. So it's 12 plus 30. 12 plus 30 is 42. So when the time equal to 14, the distance should be 42, which is like somewhere here. That is the thing. So this is basically the summary of what we've done. This means that the distance equal to the velocity 1 times the time. And this t, this means that when the time is less than 5, you do this equation, do this formula. This means when the time is more than 5 but less than 10, you do this one, d equal to v2, velocity 2, t minus 5 plus d2. When the time is less than 5, more than 5 but less than 10. And for the third one, you just do this equation when the time is more than 10. That's what this means. And also distance is equal to the sum of the rectangle areas. So let's look at this. So let's say the speed is 1 and it's 3. 1 times 3 is 3. And to make a rectangle, it's just a times b or something times something. So like 1 times 2 is a rectangle. So this is, you get the distance is actually the rectangle. So look at this. So this rectangle is 1, 5. The time is 5 seconds here, and the speed is 1. So 5 times 1 is 5. That's the distance. But 5 times 1 is also a rectangle. You can see the rectangle here, like this right here. That we just color it in blue. That is a rectangle. And that is actually the distance, because 1 times 5 is the distance. Because the speed is 1 and the time is 5. That's actually the distance. So the rectangles are actually the distance. Now, as you can see here, this speed graph is broken into many different rectangles. Each one of these rectangles is v times delta t. Delta t just means the changes in time. So like 0 to 1, the changes in time from 0 to 1 is 1. And the velocity here is 1 as well. So the velocity 1 times the change in delta t, or the change in time, 0 to 1 is 1. 1 times 1 is the area of this rectangle here, which is 1. The area of the rectangle is 1. And the area of the rectangle is equal to the distance. So the distance at time 1 is 1. We can see more clearly if we do this. So now the speed is 5 meters per second. And then the changes in time from 5 to 6 is 1. So you do 1 times 5, because that's the speed, will give you 5. So that's the area of this rectangle right here. And then the area of the rectangle is equal to the distance. So the distance for time 5 is 5. So as you can see here, the rectangles fit perfectly under the speed curve, but sometimes you might get a speed curve like this. The problem with this speed curve is the rectangles can't fit perfectly under the speed curve. There's a little bit poking out, but then we use the equation A area equals to the limit dt goes to 0, the summative of v of delta t v of t times delta t. But that's too long and mathematicians don't want to write that. So the shorter way is A equal to intergraph. Intergraph is just a shorter way. It's just a symbol of limit dt goes to 0. Integral v of t times dt. So that's just a shorter way of writing this. So we use this equation because we want dt to get smaller and smaller. When dt gets smaller, the things poking out will also get smaller. So when dt equals to 0, there will be 0 things poking out. Think, when dt is like 0.1, there will be 0.1 thing poking out. So we want dt to get smaller so we can fit perfectly under the speed curve. So now you know how to do this stuff. Let's get on to coding integration. So now we're going to be doing coding. So the first function here is going to be coding the first leg. So first we do the function distance1, which is just the name of the function. We'll call it distance1 because it's an easy name. So this is basically just the function for the first leg. So here it says the value of v is always 1. And then when you type in this, it says v times t, which is 1 times t. We always give you the distance. So first we type in the distance1 function, and this here, right here, is the time. Because this function already knows when we call it that the velocity will always be 1, because as it says here, value of v equal to 1. So if we change this to 1, it shall give us 1. Let's change this to like 5, it should give us 5. And if let's change to 10, and it will give us 10. This is because this is the first leg, and it's just maybe 1 meter per second. Its speed is 1. So this is the distance function, the leg 2. So this function's name is called distance2, but you can obviously name it anything you want. So instead of the value of 1, is now the value of 5. So the speed is now 5. So v times t is now 5 times t. So here the same thing is like we call the distance2 function, and this is the time, same is the time. So I just type in 6, so it should be 5 times 6, which is 30. And let's just type in a random number like 7. So 7 times 5 is 45. 35, I mean. So this function right here is basically adding the distance1 and the distance2 function. Here it says if t is smaller than t1, which is 5, because it literally says t1 equal to 5 here. So if t is smaller than 5, then you use the distance1 function, which is basically the velocity will be equal to 1. But if it's above 5, if the time is above 5, then you use the distance2 function. This d2, this line basically means that d2 is the distance2 function, which is t minus t1. So here we're just plussing the distance1 function plus the distance2 function, which will give us d12. So this function basically just adds the distance1 function to the distance2 function. So like in the first 5 seconds, let's say we put 3, it will travel 1 meter per second. Like 3, because if we give it 4, it will travel 4. If we give it, let's give it 2, and it'll give us 2. But if we go above 5, like let's say 6, it will give us 10. This is because the first 5 seconds is from second 1, it travels 5 meters. So 1 times 5 is 5, which is the distance for the first 5 seconds, or like 1. but this is the first 6 seconds and not the first 5. So you need to use the distance to function, which will add 5 for one, because it travels 5 meters per second for 1 second. So it adds 5 to the distance, which will equal to 10. Another example of this is we can add here, let's say 8. So here is equal to 20 because the first 5 seconds is 5. But then you plus 15 because it traveled 5 meters for 3 seconds, which is equal to 13. This is equal to 15. Which is equal to 15. Then you do 5 plus 15, which is equal to 20. So what this function does is basically plot the thing on the graph. So here is from point 0 to 10. So at point 0 it should be 1, 2, 3, 4, 5. But at second 6 it should go up to 10. At second 7 it should go up to 15. And second 8, 20. Second 9, 25. And second 10 is 30. We can also see this if we put the thing like here, 10, and it shall give us 10.0. 10, and it will give us 30. And so this function is basically applying the distance 1, 2 function to the t, which is 0 to 10, which is the point 0 to 10. So now we move on to the distance 3 function, otherwise known as the length 3 function. So the length 3 function is basically the value of v is equal to 3, and you do v times c, similar to the other one, and you return d. So we can try this out. First, we call distance 3. We put a bracket, and we can type a time. Let's say 4.0, you put a bracket, and it'll give you 12, because you times 4 times 3. Let's suppose we change this to 9, it'll give us 27. So this is how that function works. This function right here though, it adds the distance 1, 2 function to the distance 3 function. So here we can see that the value of t2 is equal to 10. So if t is smaller than t2, then you use the distance 1, 2 function, which is the one up there that we just coded. This one. But if the t is bigger than 10, then we use the d3 function, or it can be written as d3 can be written as distance 3 function, or t minus t2, which is basically the length 3 function. So the value of d1, 2, 3 is equal to distance 1, 2 plus d3, which is return the distance d1, 2, 3. So we can see this function in action by, let's plot some points. Let's type d underscore 1 d underscore, let's write d underscore 1. So short word for distance 1, 2, 3 can be d1 to 3, because I'm not bothered to say d1, 2, 3. So first we put the thing distance 1, 2, 3. So let's just type in distance 1, 2, 3. So here we can see that we put 1 and it'll give us the same thing, just 1. We put like above 1, it'll just give us 20, like the original. But if we put above 10 here, it will actually give us something different. 13, 39. Because now this, let's make it easier so it's easier to see. Let's make it 12. So 36. So we know that the first 2 is like so the first 5 seconds is 1, 2, 3, 4, 5 because of the distance 1 function. From 5 to 10, it's so it'll be 25. So 5 plus 25 is 30. But the other 2, he's traveling for 3 meters for 2 seconds. So you plus an extra 6. This is why we get the total 36. We can make this to the distance 36. We can change this to another number, let's say 11, and it'll be 33 because it's the same thing, but you minus 1 second, so you run 3 seconds less, which is 33. So this function right here, the one below the answer reference D123, is basically just plotting the function. So like 1, 2, 3, 4, 5. And it's also applying the distance 1, 2, 3 function to the points t 0 to 20. So here we can see 1, 2, 3, 4, 5 as usual, and then we go up to 30, which is the same as right here. But now we have a leg 3, which is this leg. So this leg actually goes up to 60, which is the third leg. So to give you the examples, this chart is actually real. As you can see here, is at time 11 is 33, like here. So at time 12 is 36, and at time 13 is 39. So that's how you prove the chart is real. And this thing is basically the speed graph for this distance. So as we saw earlier in the slides, there was a speed graph for that distance graph, and it is this graph. So this basically means if t is smaller than 5, then you need to return 1, always 1. If t is smaller than 10, then you always return 5. And if t is bigger than 10, then you always return 3. This is basically what it means. That's literally all it does. This is just plotting onto a plot. Using Plotly is like a coordinate system, and scatter puts the points in its place. So here we can see that it is these things. But as you may notice, it doesn't quite match the thing. That's because we used 2 big rectangles. So if we go down here, we can see that we only use 20 points, but we can change it to like 200 points. As you can see, it is much more accurate than before. This is because it has smaller rectangles to work with, so it can put smaller rectangles in its place. So if we change it to like 2000, it is not that accurate, but it's a very accurate thing. So let's just change it back to 200 because it's the best one. So now, as you can see, it is way more accurate than before. So after we explain this function, we'll go on to this function. So this function has 3 values of v. Speed, which is velocity or speed is the same thing, but velocity is just a fancy word of it, so we'll use that. So the first value of velocity is 1, the second one is 5, and the third one is 3. This means whenever the time hits 5, then it'll use the second velocity, and when the time hits 10, it'll use the third velocity here. This means if t is smaller than 5, then you do the v1 velocity times the time. If t is smaller than 10, then use the v1 times time plus the second velocity times t2 minus t minus t2. If it's bigger than 10, then you do the first velocity times t2 plus the second velocity times t3 minus t2 plus the third velocity times t3 minus t2. These t3 minus t2 is basically just the leg, like leg 2 and leg 3. So now we're going to be teaching you how to do the integration. So first we name the function distance 1, 2, 3b. And you can name it anything you want, but we're just going to use this. And we're going to make a dt1, which means the rectangle's width is going to be 1. This basically stands for, so here we have speed, we don't need this, so here. So we're going to have, so dd is a rectangle, so we do dd plus dd plus dd plus dd I times. Because we can't do dd times I because the dd is constantly changing. So we do the total distance plus dd, which will give us 1, 2, 3b. So when we plot this, we can see that at time 10, it's going to be 32. But it's not very accurate. as you can see, when we did the other method, one times it is 30 because that's the most accurate answer. But this one is only 32 because it's 32 because the rectangle here are too big. So we're gonna write this in a different formation like this, and we're gonna change the width of the rectangle to 0.1. Right now, when we go to 10, it's gonna be 30.1. That is closer to 30 because we changed the size of the rectangles. We can also change again to 0.01, which will get us even closer to 30. So we can change this to like 0.0000, and let's just change this to 0.01, and it will be even closer than it was. So that's how you compute the